and welcome everyone. I will start with asking you some questions because this presentation is a little bit of follow-up of some previews. So how many of you have seen the keynote from Paul Santos talking about Project Babylon? Yeah, probably most of you. How many of you have been on the talk from Anna and Liz about the GPU-ready AI models? Yes, some of you. And how many of you have seen today's Paul's presentation about Java and AI? Yeah, also some people. So that's great. But as I said, this is kind of follow-up, a little bit deep dive. I'll try to show you Babylon from a different perspective. So my name is Adam Sotona. I'm a member of Java platform group at Oracle, and Project Babylon is part of my life for quite some time. So this presentation is a practical case study we did to prove the concept of the code reflection in Project Babylon. If this is going to the right direction, and it ends up in something that you will see in the next couple of minutes. So one of the goals was try to go as far as we can with Project Babylon. So if you can go from Java sources up to the running AI model, and that's exactly on today's agenda. So we will go step by step. I would like you to understand, to take step-by-step understanding how this proceeds. There is no magic behind that. So first, we'll look at the Java code model. It's how it works, how it looks, what does it represent. So you will become a bit more familiar with it. Then we will show what can we do with the model. We'll show it on the partial evaluation transformation. So we'll show the transformation of the model and how they are useful. Then we'll leave the Java space and show you that the code models can model also foreign programming models. In our case, it will be ONNX. If you are unfamiliar with ONNX or with any of the technology, it doesn't matter, and I will try to explain it step by step. So there are several pieces of puzzle we need. I already mentioned the code reflection part of the Project Babylon that enables all the functionality, but it would be not enough to leave Java world. So we prepared Java ONNX script library that will help us with the second half of the path. All this will be demonstrated on 3 examples with increasing complexity. So we'll start very simple. Our first example will demonstrate just the basic code reflection. And but for you who haven't seen yet anything about the Babylon, so let me remind you some details about that. In Project Babylon, we want developers to model Java using all the power of Java, and we don't want them to embed foreign code or write some ugly Java code that would mimic foreign code models, foreign programming models. So the challenge is to go from the models written in Java, as you are used to as a Java developer, where you are familiar with it, you have all the tools to code complete it and all the helpers, and go to the foreign code model on the background, so you don't need to know it. However, let's start slowly. We'll start in a pure Java domain. This is the simplest example. We have method computed weighted sum of an array of 3 floats. The weights are here considered as computation constants. There are no custom libraries, no external tools involved, just Babylon and Java. In our first example, we would like to reach some kind of alternative version of our method. This is improved way of writing it. The loop is unrolled here. The constant, the weights are embedded as constant. The whole code is linearized. However, this way is not the best practice to write the Java. So we use it just for demonstration. So how to reach from one version to the other version of the Java code? Yeah, you probably already can guess it's using code reflection. Even this is not a typical usage of code reflection. It helps us to understand the basics without any distraction of foreign technologies. So first, we need to tell Java C compiler that we like to have the code reflection out of our method. So we annotate it with code reflection, and compiler will include the code model in the class. So it will be accessible for us as for reflection, particularly. Down you can see how to obtain it. Yeah, the entry point is the op class for us. So there we can get the code model of our method, as you are used to use reflection in Java. So there is no magic behind it. And anytime we can ask for textual representation of the code model, which looks like this. And here I have to mention that this is not a new language. Yeah, don't treat it as that you would be writing a text like this or modifying. No, this is purely for our visualization, so we can see it. We always access the code models through the code reflection API, like it's not intended to be manually tweaked. So now let's go step by step through the parts of the code model, what they mean. I've highlighted for you the code model itself. So all operations are in blue. The first operation represents the whole method we have. It has a nested body, that's the whole part in the curly brackets. And it starts with a symbol in black color. These are the operation attributes. So method name is one of the attributes. So you may see that it's the name is stored in the model as its attribute. In round brackets, you may see the method parameters, and behind that there is a return value. It's just to know what you see in our examples. All types are highlighted in green. Most of the types in our model are prefixed with Java type. That's because Java code model actually can contain only Java types and core types. However, that's not the limitation of the code reflection. It may model foreign types, foreign operations. So this is prefixed by Java type. Values are colored in red. They start with the % symbol. They are just numbered, and they are like interconnection between the return from operation and argument of other operation. So you can visualize it as a graph. Some of the operations are nested bodies. Function operation, that's our top one, has one body. That's the whole body of the method. Each body can have multiple blocks, but in our cases we don't see more blocks. There is just one block. So just has to mention that the body consists of blocks, and in each block there are operations. Our function body contains 6 nested operations, and we will go a little bit about them. The first one is variable declaration. Not everything matches exactly Java one-to-one, because, for example, in Java, if you have parameter, it automatically represents a variable. In code model, you have to explicitly declare it. That's like no magic behind that. All the other parameters are in code model just regular values. Next two operations are again variable declaration, but this time with initialized with a constant value. So you may see that again it splits into 2 operations. One is taken as argument of the other. So just to get you more familiar. This one, Java 4, is much more interesting for us. It represents kind of high-level Java operations, which have multiple nested bodies, which model like more complex Java structures. And this particular Java 4 operation has 4 nested bodies. The first one corresponds to the loop initialization. You may see that each of the body has its own operands and own return values. In this case, the initializer doesn't have any operands, but it returns a variable. So it creates and returns our I variable. So we may hand over the variable references through the model. There is also one interesting operation there, the yield operation that represents one of the terminal operations which terminate the blocks and the body in our model. Second, nested body corresponds to the for loop conditional expression. So in this case, it takes as an operand the variable, and it returns a Java Boolean type to indicate whether we would like to continue with the loop or end it. Condition nested body takes the counter variable, and inside you may see the operations corresponding to the highlighted source code part. Third, nested body corresponds to the for update. Here is interesting that you get the variable as operand, and there is nothing returned, there is a void return. So the variable is updated using varStore operation inside that block. Fourth body, that's actually the main body of our loop that we are interested in. It also accepts our counter variable, and there is also one more representative of the terminal operation, that's the Java continue, that indicates that the loop should continue regularly. So I hope that this helps you. Yeah, there are more operations inside. This group of operations are representing the loading of the value from the array. Another 3 operations are loading weights from the field, and it's multiplied, added, and stored in the sum variable. So it's pretty straightforward. Last operation of our method actually loads the actual value of the sum and returns it. Return is another terminal operation we use in our models. You've been watching all these, just I hope not to make you sleepy, but to understand what you are looking at. Now we will look about the possibilities we have to working with the model, specifically how we can transform it. So as a use case or example, we will use the partial evaluation transformation. It's part of the code reflection of the Babylon, so you can use it. And what does this do? Down you can see how it's invoked, but it may change here. You know, it's evolution of the API, but you technically just pass model to transformer and get back transformed model. So on the right side, you see already transformed model. This transformation will help us to get like more compact version of the model. It unrolls the loops. It evaluates the constants. Yeah, I mentioned it unrolls only loops that are constant sized, that can be like fully unrolled. It evaluates the constants, including the weights that the field that we consider as constant. It's according to our configuration, so this is variable. So we will talk about the details in the next couple of minutes. So our counter variable is complete. It can reach only specific states, only 0, 1, and 2. So it's perfect candidate for unrolling the whole loop and replacing all the variable excesses with constants. Pretty simplified. Unrolling means that the body is like repeated every time with a different constant values, and it's kind of linearized. This is, by the way, very welcome effect for our purpose. Array load operations are just repeated, unrolled, but instead of taking loading the counter from variable, they take the constant. So they stay on the place, but they are just multiplied. Weight fields, as we decided to make them constant, so they are evaluated and they are embedded as a constant. So we save a lot of Java-specific operations here. Multiply operation is multiplied. Add operation is also multiplied. So as you can see, it's simple. And a very nice side effect of this is not just that we removed all the nested bodies, that we removed the Java for loop, that we flattened the code, but we also removed all the variable use from our model. So it's currently in the SSA form, like single static assignment form of the model. So it helps us to work with it much easier with next steps. So we are done with our first example. It's not magic, because we get a model from our original code that's much simpler. And if we ask for a code reflection model of our alternative version of the source code, we get exactly the same. So we reach the same state by the transforming of the code models. So what to do now with the model? Yeah, you may ask, like, should I generate a Java out of it and recompile it? No, that's not necessary. Babylon contains the bytecode generator. You may ask it to generate the bytecode of the specific model for you, and you may get it in a form of a method handle in this case, and invoke it. So that's it. So you may do various transformations. This was just an example when we partially evaluated it. So now let's proceed with something more beefy. We will include the ONNX technology in our examples. Yeah, how many of you don't know what's ONNX at all? Okay, so ONNX stands for Open Neural Network Exchange. It's kind of open standard for packaging, sharing machine learning models. Think of ONNX as a computational graph that operates with mathematical operations like mat, multiply, add. And it also includes the weights and stored constants. The operations do not work with basic types like floats or ints, but with tensors, which are kind of multidimensional arrays of basic types. Tensors are potentially very huge multidimensional arrays. With large LLM models, they are very huge and there are a lot of them. The whole ONNX model is serialized in a protobuf, according to protobuf schema in a binary form, and then it can be like distributed on various platforms. ONNX runtime is a tool that runtime can accelerate it and run on various platforms, on Linux, on Windows, on macOS. It targets CPUs and GPU versions, so it's kind of generic runtime to run the computation models. Usually the ONNX is product of export from PyTorch or TensorFlow. So it's mostly not directly coded that someone would write, but there is ONNX script where you can create your own graph directly. So we choose this ONNX because it helps us to accelerate the computation model. Because if you start to think about mathematical operations on gigabyte size tensors, we don't want to do it like in a for loops inside JVM. So accelerated model, that's like fundamental core of actually, I think most of the machine learning models today. Maybe there are some exceptions. So yeah, and if you've seen yesterday's very nice talk about math behind AI, so you probably know more than's necessary for this session. So for you, it would be enough to understand that the model is a kind of computation code and weights, including packed and accelerated for computation. So let's modify our previous example just a little bit. Not much big difference. We will replace, we will replace just the basic type with the tensors. And yeah. So what's necessary to do that? The first part of the puzzle you already know, that's a code reflection, but for second part we need to include a custom library, Java ONNX script library. Now let's step aside for a while and explain what the Java ONNX script library is. Yeah. So ONNX represents for Java developers like two challenges. ONNX is a binary file format that we need to generate, and ONNX runtime is an external native library we need to communicate with, to operate, to execute. So Java ONNX script library is a product of case study that we try to face both challenges. We have to say that it's only a proof of concept. It's not any kind of production state. You may find it under examples in Project Babylon, under code reflection examples, to inspire how it may look like. The library consists of some core classes like tensors, ONNX-op, ONNX-type. It contains some set of transformations like ONNX transformer, and its execution part is concentrated in ONNX runtime class. So for easy access, like simply wrapped API. However, many parts of the library has been generated because we would like to save our time to don't write it manually. So for example, ONNX operators has been generated from ONNX specifications. Each of the operators is modeled as a static method of the ONNX operator class. It would be never-ending to write it manually from the specs, so we generated it. ONNX builder is also generated from the protobuf specification. We use it in ONNX script library to generate the binary ONNX protobuf files. So we need something to really export it to the binary. There might be alternative ways, of course. Ort API and Ort Gen API are generated by JExtract tool, part of the OpenJDK JExtract project. JExtract generates FFM API Java bindings from native library headers, so it saves an incredible amount of work and time. So through these bindings, we can operate ONNX runtime and GenAI runtime directly from Java without a hassle. So let's continue in our example. Because the ONNX is really a different beast than the Java, you know. So let's proceed step by step. On the right side, you may see the visualization of the ONNX model of our method, where we are heading in our second example. So first, we have again written example in Java using the API I just talked about. And on the right side, you may see its Java code model. It's very similar to our first example, except for some differences. Instead of primitive types, we used tensor types. Instead of basic operations, you see method calls to the ONNX operators. So you may identify the constant, mul, and add calls to our API, because we use the API to model the code, so now we see it in the model this way. But don't forget, the goal is not to run it through the operators. The goal is to model it and transform it and run it somewhere else. So our first transformation is very similar to what we did. We do partial evaluation. On the right side, you may see the transformed version of the model. It's still Java model, but it's just a different form. What we did, we unrolled the loop, as in previous example. We evaluated the constant, we flattened the whole model, eliminated all variables. So now it looks really nice. It's very close to, so we can generate a graph used in ONNX from this. Tensor weights are making us little troubles, so we keep them for now as loading from field. They are expected to be too big to include them as constants in the model, so we will handle them later. So once we have this, on the left side, still Java code model. On the right side, you see that this is no more Java. This is called a dialect, like ONNX-specific dialect of code model. and it's up to us or users what it will include. In this case, it only supports tuples, specific ONNX types, and ONNX operations. Yeah, there is space in code reflection to create your own dialects for your programming models for technologies you would like to connect with Java. So this is intermediate step to our binary model. How we get there? First, ONNX doesn't like unknown array lengths. So we transformed tensor arrays into tuples of tensor. So we know exactly there are 3 of them. Yeah, I talked about the weights which are causing us a little trouble. So in this case, we don't have any field or receiver instance in ONNX model. So we need to pass them somehow. So our solution might be done differently, but our solution was added as additional parameter. So the weights appeared as a parameter of our model. All array loads are changed to tuple load. This is mechanical transformation because we are using tuples instead of arrays. Constant operations, they either disappeared or they moved to attributes, because ONNX works only with tensors, if I simplify it, of course. So there are no like ints or floats going around, so they are used only in the model as attributes, so kind of definition of the behavior of each of the operation. So it nicely moved to the operation attributes. And the Java type tensor that we used to model it, we just change it to transform it to ONNX tensor type with specific tensor element type, which we inferred from the model. Because ONNX is pretty sensitive to know exactly element types inside the model. All the ONNX Java API, ONNX operators, Java API method invocations are transformed to the corresponding constant. So the way we generated it, this is the way we transform it back. So from ONNX operator constant method, you get a constant operator. And the attributes are appropriately set for that. So constant get the value float attribute 0. And that's it. Now we have, there's no magic behind it. Now we have a model that is very close to our target in ONNX. So we may directly generate the ONNX binary from that. We use the parameters and the input arguments. They map to the inputs of the ONNX model graph. The second parameter, we said it's weights, so we pass the weights and embed them inside the model. We know them because we partially evaluated them, so we keep them, and now we can store them in the model. Operation attributes are also embedded. In our case, it's just the 0. And multiply operations and their inputs and outputs, as well as the add operations, inputs, outputs, are linked together into the computational graph you see on the right side. Return, which is only one, only from flat, simple code, is the return value from the computational graph in ONNX. So that's it. We are done. And we've transformed Java methods into ONNX binary with just a few almost simple steps on background. So now we need to execute it. This is how it's done. ONNX runtime, that's another part of the library that we created, does all this stuff on the background for us. So all the transformation steps that we just described, you just pass the lambda calling your method that's annotated by code reflection into ONNX runtime execute. And it's not executed in Java. It's passed all the transformation I've just described, and it runs in ONNX runtime through FFM API. That's it. So what can we do more with that? This was just a second example. So now let's squeeze much more from the technology we just seen, and let's try to code an AI model in Java and run it in ONNX. But first, I don't know how many of you are aware of how the LLM model's inference process works. Yeah, I had to learn it by myself as well. So user input, if you prompt some AI, it's first tokenized. The tokens are converted to their numerical representations in tensors in our case, and the embedding is the process that maps the tokens to our multidimensional space, let's say, and the model that runs the model process produce kind of probability distribution of the next token that's kind of output of the process. It's called logits. I'm not an expert in that, so please correct me if I said it wrong. And there is a sampling which needs to select the best next token based on the probabilities, and it's added to the sequence until there is a decision that the output is complete. So then the tensors with all the logits the tensors are decoded into tokens, and tokens are detokenized into human readable text form. So this is kind of high level structure of the AI brain. However, we are going to focus only on this part, the core part that does the actual thinking. We will model it as a method, so-called transformer or forward function of LLM model, and the rest will be handled for us by the ONNX-GenAI runtime. So we will not code the tokenizer and embedder and these things. So just a brief look what's inside. That the function, the transform function, consists of multiple layers. The layers are structurally identical, but they have like individual inputs, weights, and they are interconnected, and they require a lot of computational power. So we are going to enhance our previous example just a little bit, maybe more, to become an LLM model. And this is it. You may see that it almost fits on one screen. Yeah, I just cut the long lines for you. But this is the whole brain of Llama 3.2, encoded in Java in ONNX. I have to write down that it's Llama-style transformer with prenormalization, rotary position embedding, grouped query attention, gated multi-layer perception, switch gated linear unit, and residual norm fusion. Yeah. It looks like a big jump from the previous example, but actually it's not so big difference from the programmer's perspective. Of course, mathematicians wouldn't agree. It's just a bit more complex function. It's using more fancy-sounding operations from ONNX. It's using much bigger weights and much more of them, but it still fits on one slide. So this method performs forward pass through the llama model. We have one of the parameters is a tensor with our input IDs. We have attention mask, if you are familiar with the technology. We have an array of tensors. Each of it corresponds to one layer with past keys and past values. They are like cached key and value states from the previous passes through the model. I call it like short memory, but maybe it's wrong, but I like it. We use a lot of weights. I won't describe all of them. Some of the weights are global, like token weights, init weights. A lot of weights are per layer. So it's big. Most of the weights are trained. Yeah, we didn't train it by ourselves for this example. So this model corresponds exactly to the model that you can download and run. So we use it as is. Just code it in Java. There are two specific weights which are not trained, but rather deterministically computed. There are cosinus cache and sinus cache, which used for rotary positioning. But too much details. There are also a lot of constants. One of the constants is the layers. In our case, the llama model has 16 layers. All these constants are transformed into attributes of the operations, except for layers which are unrolled later. There are a lot of fancy ONNX operations used. Some of you are familiar with that may already notice that we used like some of the combined advanced, or they call it sometimes contrib operations from ONNX. I won't deep dive into explanation, but you may be familiar with some of the names like group, peri attention, matmul, and bits. And similar to previous example, the for loop represents the layers here. So we would like to unroll it. It's constant sized loop. We are also accessing the arrays of weights. So we need to evaluate and unroll these things. And there is a new kind of issue in this case, because it's not enough to return just one value from method. We need to return multiple values. We need to return logits, past keys, present keys, and present values. So we do it by modeling it, modeling as a record. So we created custom record with these, and the record is transformed to tuple. So pretty simple. So this models for us multiple value return from method. So I won't go deeply through. This is the Java model, fragment of the Java model that we get from the code you've seen. I won't deep dive into it, but it's similar, just much bigger and much more complicated than the previous example. This is example of the transformed to the ONNX dialect. You may see it nicely linearized using only ONNX operations and tuple loads. So pretty straightforward. You may notice some of the operations are prefixed with domain. That are the contrib operations we used from ONNX. They are a part of the runtime, so you may freely use it. And once we generate the ONNX binary, we get something like this. This is a fragment of it. It shows just one of the layer, computation layer of the graph. Yeah, thanks to Netron for visualization of this. Really nice tool. So now I go to the from boring part to the more funny part, so the demo itself, bring the monsters to life. Actually, I've prepared not just one model for you, but already 2 models. And you will see how they will cooperate. And yeah, to avoid speculation that if something works in one case, it's just an accident, so I created 2 of them. So let's see our first model. It's the Llama model. It's instruction-tuned Llama 3.2 with 1 billion parameters, and it's optimized with int4 quantization, if you are interested. And you may see that it contains like 16 layers. That's the constant on top of the screen. Weights correspond to what we've seen. Majority of the weights are per layer. Yeah, we use a trick to load the weights from the external data file here. So you may see the model ONNX data, that's the trained weights downloaded, and we just load it to the weights. There is no copying beside that because they are memory mapped into like external memory, like so there are no. If you communicate through FFM API with ONNX, there is no copying. We just handle the pointers. Yeah, trained weights are loaded from the ONNX data file. And here you see the forward method that you see on the previous slide. You see that that's all. We are on 137 lines of source code. That's completely brain of the Llama model. Not big magic behind that. Maybe the magic is hidden in the weights and training, that's right, but not in the structure and code. The second model I prepared for you is Phi3 Mini. So this is pretty similar, but it has a different number of layers, different weights, different lot of things. So Phi3 has 32 layers, so twice more than the Llama. It's also quantized, and it also can be easily run from my laptop. A lot of parameters differ. Again, we load the train data. We didn't train it by ourselves yet. And you may see it looks similar, maybe almost identical. There are not much big differences between these 2 models in the structure, but a lot of differences in details. The complexity of the model is similar. You may see that it's under 140 lines of sources. Yeah. Now, let's move to demo itself. I was thinking how to showcase these 2 models, so I prepared a haiku contest. So I will run both of the models, and they will be composing haiku. Yeah, so first, to make it simpler, I created a simple record of contestant. It contains the model name, color code, so you can see it in colors. Prompt template, because each of the model is using different prompt formats. It will hold the live ONNX Gen AI runtime session of the model, and it will remember its last response. Yeah. The constructor of the contestant builds the GenAI runtime session from the instance. So all the magic that we described in the previous slides happens inside this. Like it builds the instance from the instance of the model. It builds the live session. So it does all the code reflection, transformation, and exporting to ONNX and execution, and you get the session kind of pointer in this case, thanks to FFM API. And every time we prompt the model, it's formatted according to the model. It's formatted, and the session is prompted, and response is kept inside. So we can use one response from one model to put it as an input for others, so they will try to make better haiku based on what its competitor did. Main part of the demo is that we just create it in the confined arena. If you already heard about the FFM API, how it works, we create two contestants. One is the llama. It will use the blue color, specific llama prompt format. Phi is the other contestant. It was purple color, different formatting. So the main contest starts with the kickoff. And to be more interesting, I added kind of initial contextual information that our ankle's full favorite color is blue. And we will test if the models will keep that information through the whole contest at the end. Otherwise, they are instructed that this is a contest. They will take turns to compose haiku, and they're supposed to start writing the first one. The contest goes in 5 rounds. And each time the response from its competitor is added with information. Now write a new, better, and unique haiku verse. So they try to beat each other. And at the end, we will ask, like, what's the favorite color of our uncle Fu? So let's try it run. Oh, what happens? Okay, we'll switch to yeah. Now you found me that I had prepared a screen recording of that. Doesn't matter. Here is live. Hopefully it will work the same as the recorded version. So now let's start it. As a debug prompt, you may... Oh, it's not visible? You see a different content than me. There is some technical obstacle because you don't see the output window. Why is that? Oh, it's been hijacked by... So let's start it again. You may see debug outputs of the models as they appear during the during the generation and transformation process. Now the binaries are composed, and you may see the kickoff round. So first response, so they are composing some verses of haiku, which you may enjoy, but they are not so important for our test. And after round 5, Llama answers, yeah, blue. The favorite color for uncle is blue. However, Phi says, Uncle Fu favorite color is not specified in any public domain information. Yeah, but we did it. If we look at the Phi model, if we look at the contest, yeah, we specified initially that favorite color of Uncle Fu is blue. So what can we do with that? It probably doesn't have enough big context. I call it like short memory. So let's look at the Phi3 model. Look at the constants we have, and yeah, we have a context size only 4Ks. That's too small. So during the contest, the information's probably rolled out, and the model just forgot what's been initially told to him. Let's look like where the constant is used. So it's used just to initialize it's one of the dimensions of the cosinus and sinus cache. And as I told you, cosinus and sinus cache, it's not trained stuff. They are not trained weights. They are generated. So we may get some better ones. So let's improve the model. I will increase it like 32 times. And of course, I will need to use large cache data. I prepare it, of course. But it's I didn't change any trained weights. I just modified the structure and sinus and cosinus cache of the Phi3 model. Let's try to execute the contest again. Again, it's compiled, transformed, generated. And the contest begins. You may enjoy more haiku verses. And after round 5, yes. So we improved the Phi3 model. Oh, improved. It's for some price. Yeah, the computation is more complicated. But yeah, we changed the model actively. We changed the structure, and we improve its context size. So now it fits, and it remembers the initial information. So that's a kind of proof that you cannot just code the model. It really works. You can really modify, play with the tools. Most of the stuff you will need training for that or retraining, but that's a bit out of scope for this. So that's it. That's almost the end of my presentation. Let's summarize just some key takeaways. That we shown the code reflection is very powerful to use Java for modeling, like foreign programming models. In our case study, it's been ONNX, but it can be almost anything you can imagine. That you may use the code reflection transformations as small steps to bridge Java to something that's really far from the Java programming model. And each of the steps is not so complex. So it's a very powerful tool to don't necessarily create the moonshots, but increment, like deterministic transformation of your code into something that will compute somewhere else. And the synergy with FFM API is really huge. So if code reflection can help you to model some foreign programming model, so FFM API can help you to run it seamlessly with minimal effort. So from my perspective, Project Babylon opens doors for Java developers to many, many, many domains where Java is not yet so popular or at all available, presented. And just construction of the AI LLM models is just one of the cases. You can imagine many more of such proof of concepts. And at the end, invitation to Java 1, where you may, if you can visit it or maybe later watch the videos. So I'm over time, so thank you.